Hey guys, it's Mr. Ross. I just wanted to give you guys some notes for your chemistry unit. Um, Real quick, I just wanted to let you know I've taken on a student teacher, and so I'm going to actually have that student teacher do your guys' notes for today. Um, had this person go look up a little bit of the history. Hopefully, they're a little more entertaining than I am. Um, so we're going to actually turn it over to him here. Hello, class. This is Mr. Dynamite. I'm going to teach you guys today about chemistry. My normal areas of expertise include breeding animals for their skills in magic and martial arts, but I have instructed myself on how to teach you guys about the history of the atomic model. I would like to give credit to Mr. Doug Forrest at North High School, who put these notes together that I will use. The first thing I must do is I need to make my cursor bigger because I will have to point some stuff out to you guys later. My brother Kip showed me how to do all this. He learned a lot while he was chatting online with babes. He said go to your preferences. I think that will probably be big enough for my cursor. Boom. View. Oh. Okay. Today we are going to be reading about the history of the model of the atom. The idea of the model of the atom is something that has gone all the way back to Greece around 400 BC. This is Greece. Who would have thought they were going to be doing all this boring stuff talking about this junk when it's so beautiful outside? They should have just gone out and kicked a soccer ball or something. There were these two guys named Aristotle and Democritus. And Democritus is on the left. He thought that atoms existed. However, Aristotle thought that there was no evidence for the theories. The two argued vigorously, and Aristotle disagreed with Democritus. Aristotle had a better reputation because he had sweet skills and stuff, so people agreed with him. And it seems that Democritus was rather upset about this, as you can tell by his bust. His face looks rather nasty, which may also be the reason why people didn't like his theory. This resulted in the idea of the atom being wrong for approximately 2,500 years. Thank you. In the 1770s, Antoine Lavoisier, who is this man with the wonderful white wig, and he is in color, he discovered that the law of conservation of matter says the matter cannot be created or destroyed in a chemical reaction. Mass of the things you start out with, which is called the reactants, is also equal to the mass of the things that you end up with, called the products. He took a bunch of stuff and he put it in a glass box and he burned it and he weighed it before and afterwards. And he found that the amount of mass before he burned the stuff was the same as the mass that he burned afterwards. And so he thought, hey, even though there's just ashes, other stuff must be there too. It must be a gas. And he was right. Anyway, if you guys look at your notes, it says this example, it says C, which stands for carbon, plus an oxygen molecule, which is made of two oxygens. If you add those together, the thing at the end is made up of two oxygens and one carbon, which says that the law of conservation of matter is true. Then we come to this guy who has a ponytail named Joseph Proust. I don't know how to say his name. Wikipedia didn't give me that information. Anyway, Joseph Proust said that a compound that contains the elements in exactly the same proportions by mass, no matter how much or how little of the compound you have. So if you make iron 2 oxide, you will have 1 oxygen and 1 iron, so the ratio would be 1 to 1. But if you make a different compound, the ratios will be the same for the entire compound. The proportions are always in whole numbers. So for example, if you have water, there are 2 hydrogens for every 1 water. 2 hydrogens for every oxygen molecule. You would not say that there is 1/2 oxygen for every hydrogen molecule. You cannot have half an atom. If you didn't know that, then you're a flippin' idiot. Turn to the next page. This bespectacled fellow is J.J. Dalton. No. This bespectacled fellow is John Dalton, not J.J. Dalton. Flippin' idiot. John Dalton said that all matter is composed of atoms and that atoms are indestructible and cannot be further divided into smaller particles, which is wrong. He's flippin' wrong. But he didn't know that. All atoms of the same element are identical, but atoms of one element are different from atoms of another element. Element. Ugh. So, all oxygen atoms look the exact same. All sodium atoms look the exact same. All hydrogen atoms look the exact same. If you're the same atom substance, then you look the same as the same thing. It's kind of self-explanatory. Then we have this other thing with Dalton's work that says all matter is composed of atoms. I think I already said that. This is Dalton's theory. If you have a molecule of oxygen and a molecule of hydrogen and another molecule of hydrogen, then they can create this compound that is made up of all of those things together. His atoms are really boring. They're just like flipping balls and stuff. There's a red ball and 2 gray balls, and it's not very cool. Anyway, then comes this bespectacled fellow named J.J. Thomson, who also has a pretty sweet mustache that I think my brother Kip is following. And in the 1800s, he found out that there are these things called cathode ray tubes, and they have like a flow from a positive to a negative side. And so he figured out that they must be negatively charged at some point in an atom. So J.J. Thomson, with his work with cathode rays, figured out that there must be these things called electrons, which are part of the atom. He found that they could be deflected by a magnetic field, and so there must be positive and negative charges inside of atoms. This is his model of the atom, which is right over top of his face. He figured out that atoms were just these big clouds or seas of positive charges with these tiny negative charges just stuck in there. This is called the plum pudding model. We don't eat very much plum pudding in the United States, but it's some kind of weird bread food thing that has plums in it. So here's all the bread that's in blue, and then these little plums that are yellow. The plum pudding model. It's very cool, I guess. Anyway, then comes this young dashing fellow named Ernest Rutherford. And in 1909, he did experiments to figure out more about the atom. And here's what he did. He took a look at gold, and he shot all of these hydrogen particles at them. They're just positively charged particles. They're protons essentially. And he shot it at gold, which sounds like it's really expensive, but apparently it's not. And so what he did is he shot it at the gold, and then he was able to measure what happened to it. Ugh. I gotta flip my notes. What Ernest Rutherford found, which is also displayed in this picture, is that 1 out of 18,000 trials showed that the particle bounced straight back at the atom. That would be this one. And 8 out of 18,000 of the particles were deflected slightly to the side. All of the other ones went straight through to the other side on this measurement detector thing. This is kind of weird. So here's what he found out. He found out that atoms of gold, and therefore other atoms, must actually be filled with lots of open space. And he figured out that because these positive charges were going straight through, there's lots of open space in the atom, they bounced straight back when they were hitting other positive charges because positives reflect other positive charges. And so that would be what we call the nucleus. And the nucleus must be really small because only 1/8, 1 out of 18,000, deflected back. Then, because 8 out of 18,000 deflected slightly to the side, that means that there must be some negative charges that are not right in that open space or in the center. And so they kind of pull it to the side because opposites like the negatives will attract to these positive charges coming out of this radioactive source. So here's the model that Ernest Rutherford came up with. He came up with there must be a central area that has lots of positives, and that's what the 1 out of 18,000 particles hit and bounced back. And there must be these other floating negative charges, and those negative charges are just scattered around in some kind of a cloud. And yeah, that cloud was deflecting 8 out of 18,000 of those. And then, do you need help, Napoleon? I got this, Mr. Ross. And then there's lots of open space, and that's why most of them went straight through. Okay, Napoleon, I'm going to step in here for a second. So, since positively charged particles repel other positively charged particles, okay, this central area right here, this is what was repelling that one particle back, and I know Mr. Dynamite already said that. And this was kind of the evidence that the plum pudding model could not have been correct. All right. The plum pudding model, again, was saying that you have an atom, which is just this big blob. If it was truly a big blob, then we wouldn't have had all those particles that go straight through. Again, it was something like 17,991 of the particles went straight through out of the 18,000, and only 9 of them got moved some other way that didn't go straight through. Again, the ones that bounced back were hitting this central nucleus. So the nucleus must not take up very much space. In fact, the nucleus takes up very, very, very little space. I had a college professor once in high school, in college, not high school, and he told us pretty much that if you took a big basketball and you put it in the center of like Ohio Stadium, if you go all the way out to, I want to say the first, second row, that's about how far the rest of the atom is. So most of it is just empty space, and that's where all those electrons would be floating out. The electrons, again, are floating in this big area. So we have like this cloud model right now, and that cloud model is kind of saying that most of the space is empty. So again, most of the space is empty, and again, this is because some of it got deflected. When a positive would get near one of these negatives, it would get deflected, when it hit the center, it would bounce straight back, but most of the time the electrons were going straight through. Okay, so let's take a look here. Most of them are going straight through because it's empty space. Some of them get deflected because positives attracted to those negatives and got bent a little bit as they were shooting through. And then some of them just got shot straight back because they hit the nucleus, and that was just purely by chance. So, Mr. Dynamite, do you want to take over here? Yes. All right, go ahead. That's the model again. Okay, before we go on to this guy who's Niels Boring, the mass of all atoms except hydrogen was quite a bit less than the combined mass of protons and electrons, and so there must have been a third subatomic particle. When they measured the mass of these different atoms, they found out that since protons and electrons balance out the charge of atoms, the third subatomic particle must be electrically neutral. I'm going to go back. They pretty much said that all of these negatives should collapse in on these positives, and so there must be some neutral charge thing in here that's keeping the balance of the force. Kind of like Luke Skywalker. But it wasn't until the 1930s that they found the neutron, which is that neutrally charged particle. The neutron has about the same mass as the proton. So when we note that it took much longer to discover neutrons than electrons, why was it? It's because there was no charge for the neutrons. All of these things are charged, so we found stuff with the Rutherford experiment. Now we get to Niels Boring. Niels Boring is kind of like the Danish version of Brian Williams. In 1913, Niels Bohr realized that Rutherford's model would have electrons collapse to the nucleus, and he's the guy who kind of figured out that we have these planetary models of electrons where electrons exist in different energy levels. This, combined with the discovery of the neutron, allowed us to have a better model of the atom, which is where we are going to pretty much end up today. Here's an example of a Bohr model. The Bohr model pretty much says that in the center of the atom there is a nucleus. This one is argon. It has 18 protons and 22 neutrons, and they're all in the nucleus. It's pretty cool, I guess. So then surrounding it, it has these different orbits, kind of like planets around the sun. And in the first orbit, you can only hold 2 electrons. Then in the next orbit, you can hold 8. And then in the next orbit, you can also hold 8. When you get to higher levels, it gets a little more weird. So we're not going to talk about that crap. But if you add up all the electrons, there's 2 here. And there's 8 here. And then there's 8 on the outer shell. We call these shells or orbits. 2 plus 8 plus 8 is 18. So this has 18 protons and 18 electrons, so it is electrically neutral. Okay, this is, I think, all I know. All right, thank you, Mr. Dynamite. Everybody, just to kind of recap a couple things, we are looking at the model of the atom. It is something that is going to continue to change, I'm sure, as we get new evidence. That's how any good scientific model is. The Bohr model is where we're going to kind of end up for most of integrated science. It's the most useful for the basics of chemistry, but as you guys go on to take more chemistry, there'll be more stuff that kind of comes up that you guys will learn. One quick thing. You guys have those notes for final thoughts to remember. All atoms are electrically neutral. So if you guys take a look at like this argon here, argon has 18 protons in this picture. It also has 18 electrons. So that is why it is electrically neutral. 18 positives, 18 negatives. That gives it a charge of 0. So that first little blank there says this means that neutral atoms have the same number of electrons as protons. Okay. When you guys look at the periodic table, a couple things I wanted to point out for you. Let me just escape out of that. There we
This is ptable.com, very, very helpful for you guys just to look up information about atoms. But here you guys have probably seen a lot of this stuff before. Here, I'm going to click on hydrogen. Hydrogen right now has an atomic number of 1. Vanadium, if you look at vanadium, it has an atomic number of 23 if you kind of missed it on there. This number that's in like the upper left-hand corner there. The atomic number is how many protons the atom has. And every atom that is a vanadium has 23 protons. Some of the other stuff might change, like neutrons and electrons might change, but it's always going to have 23 protons. For boron, it's always going to have 5 protons. The other stuff can change potentially. Mass number, which is this little number right here, it's usually like a decimal of some point. Mass number is kind of like the average mass in these atomic mass units. So it's very, very small. It's not like in pounds or anything. It's the sum of the number of protons and neutrons in a nucleus for a particular atom. So you obviously can't have portions of a proton or portions of a neutron or portions of an electron. And again, electrons actually, they don't really add up to the total mass. But when you look at it, you have this decimal, and that's because we have these weird things in nature called isotopes. Like I said earlier, every boron is going to have 5 different protons in it, but the number of neutrons might actually change. So when we look at this, boron has 5 protons, and this number right here, that's the 10.81, that means that sometimes it might have like 5 more neutrons, but sometimes it might have 11 neutrons. So isotopes are the cause of these different decimals that we have. Okay, let me get on boron again here. So most likely, most of the different borons that exist in nature have something like a total mass of 11. They have 5 protons, this atomic number, and then they might have like 6 neutrons. 5 plus 6 is 11. Now again, this is not 11 on the mass here, because this mass is an average of all of the different borons that you might find in nature. So some of them might have 11 for their mass, some of them might have 10 because they only have 5 neutrons rather than 6 neutrons. Okay, and again, different atoms of the same type that have a different mass, it's because they have a different number of neutrons, and those things are called different isotopes. So like we have different isotopes of carbon. They all have 6 protons, but they might have a different number of neutrons. Okay, these different versions of the same atom, again, are called isotopes. We also have these things called ions, and ions are just electrically charged atoms. Sometimes you have a positive charge, and most of the ones that make a positive charge are over to the left side of the periodic table. And then the ones that make a negative charge are over to the right side of the periodic table. And we'll discuss those a little bit more in detail. The ones that make a positive charge are called cations. You can remember that they're cations because they are positive. You get it? Pause. I hate puns, by the way. And then the ones that are on the right side that make the negative charge, those are called anions. And again, we'll talk about these a little bit more in detail. The last little blank that you guys have in there, based on the Bohr model of the atom, you should be able to recognize that ions form when atoms gain or they lose the subatomic particle that is the electron. Okay, this should make sense, and this is the last blank, because electrons are on the outside of the atom. It's easier to lose something that's on your edges rather than something that's inside of you. It's like it's easier for you to lose some of the skin particles that fall off of you rather than like your heart just come right out of your chest or something. All right, so again, we're going to go into a lot more detail with all this stuff. Rewatch this video if you need to. There are a couple different video references for you as well if you want other resources. And again, these notes are from Mr. Forrest over at Pickerington North High School. He's an awesome teacher, so I just figured that since he shared his stuff with me, I might as well use it rather than reinvent the wheel. All right. If you guys have any questions, please email me, contact me, and we'll see you later.